Okay, so I'm saying that the first time I had in contact with Jean-Pierre was maybe in 1994 or 1995. At that time, I was a student in Paris 6. I just moved from computer science to mathematics, and then I asked him some advice about complex analysis, and he very nicely replied to my letter, talking about, I remember that L2 technique and dynamic consistent and so on. And then many times in Paris 6, in conferences, and also sometime here. And I remember that the first time I came here should be in 1996 or 7. I gave a talk in his seminar, and it should be my first talk outside my university. And I remember that here, it was my feeling that here people or is doing mathematics very serious. I don't know if local people confirm me about this, but yes, so this is my feeling. So of course, it's very unfair that Jean-Pierre passed away so earlier. But okay, so this is. So okay, so now I'm going to talk about, give a survey talk about some question that Jean-Pierre asked about 30 years ago. And then, okay, so here we go. Yeah, so this is a very general question, and I'm going to propose some solution to this question and some application. And also at the end of my talk, I will mention another question of Jean-Pierre, which seems to be very challenging. Okay, so here's the question. So it's to study the intersection of two positive closed currents, T and S, and in Higher by degree. So this question that I learned from him in this paper published in 1992 in Gazette des Mathématiciens in French. So in this paper, he mainly discussed the case of 1-1 currents, but this question. So even in the case of 1-1 current, you have seen yesterday that the problem is already very general. So then you have to you need some motivation to consider the setting where you want to define the intersection of currents. It's the same in Higher by degree, and then our first motivation was the complex dynamics in higher dimension. Yeah, even actually, even if you work in complex dynamic in dimension 1 now, you still need to study the problem. The reason is that now people study a family of the moduli of complex dynamic in dimension 1, and then you easily go to higher dimension, and then you get such a problem. Okay, so here's the that I call ideal situation. That's a guideline of what we need in this for this problem. So this is a perfect situation that if you can define it locally, if the definition is independent of the choice of coordinates, so you can define it in any form. It's very important. And the definition should be compatible with the West product of forms, so it's a smooth case. One of them is smooth, for example. And the intersection of cycles, so you have analytic or algebraic varieties. Assume that the intersection has a good dimension, so you can define the multiplicities, and then you can define the intersection. So you want your to be compatible with this one. And about cohomology, and also there are other no case, and you want everything to be compatible. And you also want some continuity as strong as you want, you can. With respect to T, N, or S, otherwise you need at least some semi-continuity or some weak continuity. Okay, so this kind of properties that you need to have for this intersection theory. But of course, restrictive is ideal situation. So for example, you can remove the first one. So okay, you can identify the intersection globally and not locally. This also okay. But definitely you want it to be independent of coordinates. At least if you do dynamic consistent, because you don't have invariant coordinates here. So of course you want it to be compatible with smooth K and so on. And the continuities that I said, want it to be as strong as you can. Okay, so let's go ahead. So here's the case of by degree 1-1. So it's go back to the work by Bedford-Taylor and Jean-Pierre, and also Oka for Simony and many other people. I have mentioned here some case that I don't directly discuss here, but okay, here is a situation. When T is a by degree 1-1 current, you can locally write T at DDCU, where U is a purely subharmonic function, which is unique to a purely harmonic function. So it's a modulo a very, very nice function, which is smooth function. So every singularity you can see for T is already in this function U. Yeah. So you assume that U is integrable with respect to S. Then you can define T with S in this way. So we have seen this in many talks already. DDCU with S is equal to DDC of the product of U with S. So here you can observe that there are two important things. So first, S is closed. So then when you compute DDC of this formulae, so the derivative of S is 0, so you just have this one, and then it's exactly what you want. And another important property is that the purely subharmonic functions are defined everywhere, at every point. It can take a negative infinity value, but actually it's defined at every point. It's very important because let's say the support of S could be very small. So if you take L1 function, for example, then you don't have value in a big set, then you cannot define U term S. It's not meaningful. But here, because the function is defined everywhere, then this is at least meaningful. But you need this to be integrable, so that the integrand is finite. So you have a current here, and you take the DDC. Okay, as an example, some examples. So let's go back to maybe Chen, Levin, and Berg for continuous case. So U is continuous, then you have this condition, or locally bounded. Oh, here I should say U is okay. U is local, yeah. So this go back to Bedford-Taylor theory, and the contribution of Jean-Pierre is a case where U is bounded outside a compact subset of a open set. So let's say the simplest case that is bounded outside a finite set. But this already is because he uses to study the long number of currents. So you need to focus the study at points, have some singularity at one point. So for the long theory. A more general case by Oka for Simony. So we can assume that U is actually bounded outside some closed set, which is pseudo-convex enough. I don't give you more precise definition here, but it's related to the Hartog theorem. So if you have estimate in some, then you have estimate on the disk, and it's similar to this set. It could be more. But let's say that if you have a set which is pseudo-convex enough, then you can check the condition using the fact that it's bounded outside this pseudo-convex enough set. Okay. So I don't discuss the purely non-polar product here. Okay, so let's consider another particular case. So assume that you have a holomorphic, surjective meromorphic map. It doesn't change very much from meromorphic to holomorphic to meromorphic, but let's say meromorphic map from X to Y, and then you want to pull back positive cross current from Y to X. So what you can do, so let gamma be the graph of this map. So you are in the a product of X and Y, and inside you have the graph gamma, and you have the two projections on X and on Y. So how formally how you can define the pullback of a current? You pull back T. So pi y is submersion. So you can always pull back T by pi y, and then you take the intersection with gamma, the current of integration on gamma, given by Lalonde theorem, because gamma might have singularities here. Okay, so then you push down by pi x. Yeah, so you pull back the current by the horizontal map, and you take the intersection, the restriction to gamma, and then you push it down. So as I said, so the first current here, the pullback of T by pi y is always well defined. So this push forward operator is always well defined under a very weak condition. So you just need pi x to be proper on the support of this current. So for example, if y is compact, then you have no problem. You can always do that. So the key problem to define this pullback is to define the wedge product here. So actually, this is a particular case of the wedge product, the intersection problem. So the pullback operator is a particular case of the intersection problem, the main equation. Okay, so some one is due to Meo, former student of Jean-Pierre. So you can always pull back it, and you have all properties that I give you at the beginning. You can do that locally. You can have a strong continuity, and so on and so on. Meo also proves that you cannot do that. In general, you cannot do that for higher by degree. So more than one, you cannot do that. So however, if you assume that all the fiber of pi y from gamma to y, if you assume that the fiber are either empty or of minimal dimension, so dimension x minus dimension y, assuming that, then you can do that. And you are also in the ideal situation, all the properties that I showed you before. So these are two cases that we can do some example for this problem. Okay, another particular case is the sizing theory due to Fourier. So it actually works in the real setting also. So, but assume here that you have a holomorphic submersion for simplicity. Assume that is you have a current on X with dimension larger or equal to the dimension of Y. Then for almost every Y, you can define the slice of current. So it's a particular case of intersection theory. So we have a current here, and then you have some map from X to Y. So have f minus 1 of Y is this fiber. Then for almost every Y, you can slice your current. And actually, it's a particular case of the intersection theory here. So it's work in the real setting. But here in the complex setting, we expect that we can say more than that. But OK, we can consider this slice as the particular case of the intersection theory. OK, so let's give some example here. So assume that we are in the case of a product of two open sets in Cn minus P and Cp. So we have the product of two domains, M to N, and you take the projection onto M. And you assume that your current is horizontal, which means that the support is, so here you have m times n, and you assume that your current is like that. So the current doesn't touch this horizontal boundary. So it's go in that direction. Okay. So in this situation, you can say more. For the Fourier theory, you can show that actually these slice, you can define this slice for every y. For every y, you can slice. Not only for almost every y, but for every y, you can define this slice. You have a good continuity, but it's not the strongest one. So the continuity is the following. So assume that you have a purely subharmonic function on the space, and you define this the integrand of this function with respect to the slice. And then you have either negative infinity or purely subharmonic function. So which means that the continuity that you have is similar to the continuity of all of pure subharmonic function. Is stronger than, okay, it's some kind of continuity for purified topology and so on, but it's a quite strong continuity, but it's not the strongest one. So these are similar to many settings that I'm about. This kind of continuity that you often have. Okay, actually, is we have a more general theorem. If you take a horizontal current like that, and you take a S, a vertical one, then you can always define the intersection, and you have some kind of continuity like that. This always, you can always define this. So somehow in the complex setting, you have a better theory, Fourier theory, than in the real setting. Yeah? This is an example of the intersection theory. Okay, so let's go back to the general problem and use some answer.
Even it's minus infinity at the fiber, it can also be.
It cannot be minus infinity.
But if you say it's a vertical current, it's vertical.
Yeah.
Suppose it's a vertical.
Yeah. Yeah. You cannot have. Take the one case. You cannot have negative infinity vertically. Okay. Yeah. This is the point. Yeah. Okay. Okay, so here I try to give you the first answer to the question motivated by some problem from complex dynamics. So let me go. I consider a particular case x equal to Pn. The setting is simpler, but the Cayley case is quite more complicated. But so I avoid to the technical issue here. So x now is Pn for simplicity. And now we try to mimic the K of 1,1 current. So using potential of T, we have potential here, but it's not as good as in the K of 1. Current is the so-called superpotential that is now. Try to mimic this approach. Okay, so omega fs is a Fourier study formed on Pn. It's a fixed, and T is a positive closed current, PP current on X. Assume that it's mass 1, simplicity. And so let's denote Cn minus P plus 1 is the set of all positive closed current of by degree n minus P plus 1, n minus P plus 1. And of mass 1. So this is so how I can. So this is a compact set, compact convex set. Let's say like that. So C n minus P plus 1. And it's compact for the weak topology, and here you can define this one distance. You can define a notion of distance. What's the starting distance? You C1. C1 test a form. So you take R minus R prime, you test a form alpha with C1 norm at most equal to 1, and you take the supremum. You can, instead of C1, you can take a C alpha for and have other notion of distance, which are in some sense, it gives you the same topology. And you have the theory of interpolation in of Banach spaces tell you that you can compare this distance. They give you the same. Okay, so you have to think of this as a complex manifold or complex variety of infinite dimension. At least in the case of Pn, you see that you can move your automorphism, you can take a branch, and so on. In the by degree 1-1 current, you have currents according to the May regularization techniques, and you can easily move your current or accepting. In Pn, you have no problem, but in a current, using his technique. In Heidegger, by degree, you can only accepting some negative loss. You can move your currents. So you can think of this as a complex variety of infinite dimension is compact and so on. So the superpotential that I'm going to define to be a function on this infinite. And you can think of a quasi-subharmonic function in this space. So, okay. So the definition is as follows. So the notation is UG. So it's similar to the quasi-subharmonic function. It can take a value in R and negative infinity. So the definition is simple. So it's a formal definition. So you want to define the value of UT at R. It's a point R here. So how you do that? So you solve this DDC equation, R minus some power of Fourier study form, and you solve the DD bar equation, you have a potential. So you can normalize the potential by asking that the mean is equal to 0. And then you define this superpotential as this integrand. So at least if R is smooth, you don't have any problem. You take a smooth potential and you take this integrand. So there's some step. You have to show that, okay, if P is equal to 1, then the quasi-potential of R is unique. Yes. Yes. No. If P is equal to n, then it's unique. But in general, the potential of R here, the quasi-potential of R here is not unique. It's very far from being unique. You can add here any DD bar closed current. So it's not unique. If you want a standard one, you have to fix some coordinates. But as I said before, you don't have to use the coordinates. So it's far from being unique. However, you can show that this integrand is independent of the choice that you make here. It's easy application of Stokes theorem. Yes, if you don't normalize it, it's like a quasi-subharmonic function, quasi-potential. You have to add a constant to your. No. No, the normalization here is correspond to the normalization of UT. So minimal is more complicated. Okay, so let's see here in this is a case of by degree 1-1. So what do? You write T equal to omega Fs plus DDC UT, and UT is unique if you assume this condition equal to 0. the mean of V R to be 0 is just to say some sense that the mean of this U is equal to 0. Okay. In the Keller case, yeah. In the Keller case, so okay, in the Keller case, you can do more or less the same here, but then the case where R is not smooth is more complicated. Because the regularization is more complicated. So, is your question? Oh. Yeah, but you can do, yeah. For homogeneous case is exactly the same. Otherwise, this one is always true. So UT is maybe not. You cannot see UT as a quasi subharmonic function, but maybe the difference of quasi subharmonic function. Then in the Keller case is okay. If you consider this kind of function, then accept it. But we want to do better than. But okay, anyway, it's more complicated. Okay, so we can worry about this notion because you have a quasi subharmonic function on infinite dimension, and then I try to convince you that we can do some analysis in this space. So let's say one of the estimates that we often use for purely subharmonic function, at least in dynamic setting. The Skoda estimate. So if we have a purely subharmonic function, or quasi-purely subharmonic function, ut here, then this integrand is always bounded by some constant, independently of the choice of t. So you see here that it's very easy to get this estimate if you don't have exponential. If you have exponential, then you have to work a little bit more. But without exponential, it's easy. Okay, so now we go back to this I call Skoda type estimate. So we cannot consider you don't have a Lebesgue measure on this infinite dimension space, so you cannot do exactly the same thing here. But we have an equivalent version. These are the following. So you consider ut, the value ut at R. You can take R smooth. It doesn't matter because the estimate should be uniform on R. So, so you take the value of ut at R. So it's easy to show by definition is that this value is bounded by R infinity without log. Without log is just by definition. You just put it in the definition, you get it. But actually, this estimate is exponentially better. So this is actually equivalent to Skoda estimate. This is the way that we use Skoda estimate in this setting. So just to convince you to do something, even you don't have Lebesgue measure on this infinite dimensional space. So it's in the case of bi-degree 1-1, it's really equivalent. You can have equivalent correspondence between. Yes. So so let me go ahead for the. Okay. So here's the answer to the question. Okay. So now we have a positive closed current S of bi-degree QQ. So we need some condition which equivalent to the integrability condition in the case of 1-1 current that I told you before. So the condition is this one. So the value of the superpotential of T at this current, you have to complete S to have the right bi-degree, but essentially it's S. You have to do the same actually in the bi-degree 1-1 case. So essentially it's S. So the value of ut at S should be not equal to, it should be finite. So this is the integrability condition in the 1-1 case. So you have shown that you have this condition, then you can define the intersection of T and S in the following way. So basically, you want to define the integrand of alpha, some test form with the smooth state form with respect to T with S. Then then you write DDC alpha as beta plus minus beta minus. Yeah. This equation, this beta plus and beta minus are not unique, but okay, you make a choice. It's independent of the choice that you make. Basically, you take the value of the superpotential at beta plus OSS minus the superpotential at beta minus OSS, and you take some correction, which is, I don't want to write down because it's not the main part here. So this is the definition of the West product. You can show that this condition is actually symmetric with respect to T and S is symmetric. If you permute T and S, you have the same condition, and then the product is also symmetric, and so on. You can have some continuity similar to the one that I told you before using test with harmonic function. So if T has bounded superpotential is similar to the Bedford-Taylor theory, then you can define T with S for every S. Yeah? So we can compare with the 1-1 case, by degree 1-1 case. So in the case of by degree 1-1, you write T at DDC of Vt plus omega Fs. You assume that Vt is integrable with respect to this measure. Anyway, so then you can define the West product. You see that it's given by this way. So you test alpha, so it gives you this Vt DDC alpha by Stokes plus omega Fs. This is a correction. Yeah? This is a correction. So forget this. Just focus on this one. Then you have this term and this one. It's exactly similar to the case of, and the computation is the same. Yeah, in the singular case, you have some regularization, but formally it's like that. Okay. Very good question. Very good question. Excellent question. So in the case of easy case, it's easy to get positivity because you can deform currents without losing positivity. In the Keller case, it's more complicated. It's not obvious at all. But according to the theorem of Wu, Wu-de-Viet is actually positive. Yes. Yeah. It's an excellent question. Okay, so as I told you, is motivated by dynamic, complex dynamic dimension. So here's one of the applications. There are different applications, but I'll give you one application. This is for automorphism of a compact Keller manifold. So the theorem is due to Cantor for K3 surfaces, and the theorem is following. So assume that you have a holomorphic automorphism on compact Keller manifold X, and you assume some condition about the action on cohomology. So basically, you have to assume that the pullback operator on the Hodge cohomology to itself is simple in the sense that you have only one maximum eigenvalue, only one of multiplicity 1, and then you can show that you denote this eigenvalue by D is a maximum eigenvalue which is unique. Then you can show that this actually the eigenvector should belong to some HPP. This you can show that. Okay. So this is the definition of P. So assume that the cohomology is simple, the action on cohomology is simple. So in this case, you have a unique positive closed PP current T plus and unique positive closed closed current T minus of by degree n minus p or mass 1, such that the first one is invariant by F, pullback of F, and the second one, okay, sorry, here is T minus, so this invariant by the push forward. And then if you take any positive closed current, let's say PP positive closed current, let's say you take a subvariety of right dimension, you pull back by Fn, by the iterates of F, and you normalize this. then you can show that it's converged to T plus exponentially fast. So exponentially fast means that you can use a test formula and you have the decreasing to 0 exponentially fast, or you can use the distance that I defined here on the set of currents, and you have the distance go to 0 exponentially fast. You have precise speed of convergence. You have the similar property for the push forward because it's an automorphism. You can show that the currents have Holder continuous superpotential because the convergence is very fast, and then you can starting from something smooth, and you can hope that you keep some regularity at the limit. Actually, the best one is a Holder continuous superpotential. And then you can define the wedge product, and that will give you actually the unique invariant measure of maximum entropy and so on, so on. I don't want to say more about this. So this the first motivation for this definition of intersection. So you could imagine that in the case of dimension 2, so you only have one currents, then you use potential and Skoda estimate and so on to get this kind of theorem. So we try to mimic this in the same way in the higher dimension using superpotential and using Skoda estimate and so on. This is the way. You can, okay, yes, technical difficulty, but mainly you can follow the case of by degree 1, okay? So there are other applications that I mentioned here, including work by De Telang, Vigny, Taeyong An, Bianchi, Rakimov, and so on. Okay, so let's let me give you another application outside complex dynamic setting related to the work, the talk yesterday. So you consider the Monge-Ampere equation, the complex Monge-Ampere equation, the classical one. So it's strictly positive. So we want to solve this equation. Mu is a given measure, and the unknown is a quasi-subharmonic function u. And you want u to be a Holder continuous solution. And the theorem, our theorem with Nguyen, say that it's actually a necessary and sufficient condition. If and only if the superpotential of u is a Holder continuous. If the superpotential is Holder continuous, then it's equivalent to the possibility to solve this equation with Holder continuous solution. And you see here that it's a linear condition. Yeah? It is known before indirectly that it's a linear condition, but here you see that directly it's a linear condition by definition. It's not clear directly from the equation, which is not linear. So it's related. I'll give you an example. I go back to Yao, Colaugier, Hiep, and Wu. So now in the manifold X, you take a Cauchy-Riemann sub-manifold, which is generic in the sense that the real tangent space generates the whole space, the whole tangent space. Then on this submanifold, you can take a Lebesgue measure, or you can take a LP density measure with p larger than 1. It's also okay. Then you can solve the equation with the Holder solution. So this is the work of this people. So of course, a famous theorem by Yao and Colaugier in the case of X for the submanifold for real hypersurface is due to Hiep, and Wu proves the general case here. So there are a lot of examples of such measure. So the key point in the proof is Jean-Pierre technique of regularization of quasi-subharmonic function. And there are a lot of work related to this. Colaugier, Hiep, Demey, Diniu, Get, Hiep, Colaugier, Zeriahi, Wu, and so on. Okay, so what I like here is that it's a necessary and sufficient condition. It's really equivalent. Okay, so now let me go to the next chapter, solution. So density of positive cross current. So the starting point is coming from maybe it's not the way we started, but later we realized that actually is similar to this one, is the Lelong theory, Lelong number theory. So for simplicity, you take two variety in X, and you consider the intersection. I mean, let's say geometric intersection first. So geometric intersection of two variety, it could be of it could be empty, of course, but it could be of you have some expected dimension of the intersection. In the generic case, you have the expected dimension of the intersection, but sometimes you can have higher dimension for the intersection. You have some dimension excess, yeah. So, so for example, if you take a subvariety and one point, so in general, the point is outside the variety, but sometimes the point is inside the variety. So it's the intersection has dimension excess in this case, yeah. So now you replace your variety by currents. So can you say that the point belongs to the current or not in the same sense, in the same sense as a geometric sense? So it's exactly the Lelong theory. If the Lelong number at this point is larger than 1, then you say that, okay, the point belongs to the current in this sense. Okay? Similarly to the variety, the point belongs to the currents, not in the sense of support, not in the sense of, but in the sense of intersection, but with dimension excess. Okay? So we can generalize it to higher dimension. So the theory here we try to do is to replace points by higher dimension varieties and try to see what is the geometric intersection in this sense. And more generally, you take two currents, two positive cross currents, T and S. So we want to define some kind of definition of the intersection of these two currents, including the case where the dimension is larger than the expected dimension. So can you say that the current S, the second current S, belong to the first current in the geometric sense? So these are ways that we try to do here. Okay, so this is a starting point. So for simplicity, we have the current S, T, and for simplicity, you assume that S is equal to some submanifold, V. And you want to define the intersection, this intersection or geometric intersection, whatever you want to understand this. So you are going to say to try to do the following. So here is your submanifold V, and you have a current here, and you assume that we have some kind of intersection that you want to see here. So the idea is that, okay, I try to dilate the coordinate in the normal direction. I dilate this, and the idea is that when you dilate the coordinate in the normal direction, the intersection doesn't change. But somehow you see the intersection better and better when you dilate the coordinate, you take the limit, and you want to see, I hope that at the limit you can see the intersection. Okay, so this is the rough idea of that we try to use. Of course, there are many difficulties, technical difficulty here. What is the meaning of the dilation here? You don't have this immediately. So, okay. So the first technical point is that you have to bring everything to the normal bundle. Normal bundle of V inside X. So you choose a good. So there's a normal bundle and the VT, Vx. Okay, it's normal bundle to V, and you bring everything here to a neighborhood of this zero section of this normal bundle. So using some tau locally, so you choose some neighborhood here, and you try to bring it to this normal bundle. Okay, maybe I have to remove this current. So you take a neighborhood of V, and you bring it some. You choose a tau good enough. You bring everything here. And here you can dilate the coordinate. So you can see, you already have some technical problems. So you have a current here, and the map is not holomorphic. It's close to holomorphic map, but still it's a real map. So when you bring T here, your current is no more positive. You cannot talk about the positivity. It's not by degree pp. But near the V, you hope that it's close to suck a current. So then you dilate the coordinate. But the current is no more positive, and so on. Yeah, so you do that. You do that. So you bring everything there, and you dilate your coordinate in the normal direction. So we try to get the limit, but actually the situation is much more difficult than expected. So Tien-Cuong long time ago proved that even in the setting of a long number, the limit doesn't exist. In general, you might have different limits, and then you have to take a subsequence. But when you take a subsequence, you have to make sure that the mass is bounded, so that you can take a limit. Yeah? Otherwise, you can go to infinity. Okay, actually, our theorem says that you can actually show that by taking subsequent, at least, you can always have limit. The mass is bounded, and the limit become positive and close. So when you take the limit, the current, when you bring there, is no more positive, but the limit is positive. You have a positive closed current in the natural compactification of normal bundle. So as I said, according to Tien-Cuong, you might have many limits, but actually the cohomology class is unique. The cohomology class of all limits you take is the same, should be the same. It's very interesting because now you cannot talk about intersection, but at least you see how big the intersection is. What is the dimension of the intersection of current? Is V, the question that, sub-question that I asked before, is V, you can see that V is a subset of your current or not. Something like that. You can say, just using the cohomology class. Okay, so now you have the projection from your normal bundle to V. And if you have a variety on this vector bundle, you can take the projection of variety, and you can have variety of lower dimension. Okay, so in this case, we can show that we can do the same for currents. So you have current upstairs. In the theory of current, when you push down a current, you have a current of same dimension. But here, I can take another kind of projection, a more geometric intersection projection. And then you can define what we call the shadow of the current on T. So the dimension can be lower. The dimension can be lower. Like you take a variety, when you take a projection, the dimension could be lower. So in the sense of current, the projection will be 0. But in another sense, a more geometric sense, you can define the projection, which is a current of lower dimension. So it's you call the shadow of G plus. Okay, so this gives you the information about the dimension of the intersection of these two currents. What is the dimension? And so on. Okay, so this is very technical. So this is what I said. Okay, so now we can define the intersection under some condition. So we need that there is no dimension excess, so which means that the shadow that you have is of minimum dimension. Because otherwise, in general, you might have bigger dimension. But if you assume that the dimension is minimal, you assume that the limit of current is unique. You have only one limit. Then you can use the theta as the intersection of T and S, T and V. So T and V now is this exactly the intersection. So imagine that T is a variety. T is a variety which intersect V. The intersection has good dimension. You dilate the coordinate, and at the end you have the shadow. The projection of this variety is exactly the intersection that you are looking for. Yeah. So for current, you can. And then you have the intersection in this case. Of course, you cannot define the intersection in the sense of current at the beginning of the May problem. But under some condition, you assume that T infinity, the limit is unique. You assume that there is no dimension excess. Then you can show that actually you can define the intersection in this way. Now, no, I expect that it should be one of the weakest conditions that you can put. Because I argue here, assume that you have some kind of intersection, you dilate the coordinates, or you expect that the intersection doesn't change. So it's a minimum condition that you need if you follow this guy. So actually, this condition is weaker than the condition about superpotential. And this due to so. And then the definitions are compatible. And this actually answers to your first question, because here it's easy to show that the current is positive. But in the first case, it's not clear. So this is a way that proves that it's actually positive in the first case. Yes. Yes. So now assume that you have two currents, T and S. So to define the intersection of T and S is you can reduce to the first case by taking the tensor product of T and S. So you can always define this. This is a Duan version of Weierstrass approximation theorem for function. So you can always do that. You can always do that, and then you consider the intersection with the diagonal. And then it gives you the definition of T with S if you are in the good situation. Okay, so this is here's the motivation of the work. So you take a Henon map in any dimension. Is a class of Henon map introduced by Sibony. So we can show that you can have T plus and T minus as before, and the West product and so on in the first theorem, similar to the first theorem. And then here we can show that sudden periodic points are equidistributed with respect to the measure of maximum entropy. So if you put the Dirac mass, okay, I forgot to normalize this. You put Dirac mass at a periodic point. You take the sum and you normalize by dividing by the mass, and then the limit is equal to mu. So we have a good invariant measure, and you can prove that periodic points are equidistributed on this. Okay, so I will not give you the proof here, but the main idea here is you have to show that okay, the measure mu is the intersection of T plus and T minus. And you can use the theory to show that this intersection is transversal. This is very important to show the theorem. You will see a little bit later. You need to show that it's transversal. Okay, to make sense to this, you have to leave everything to some Grassmannian bundle and tangent bundle and so on, and you can see that using a theory that the current are actually transversal each to other, and it's a key point in the proof. So the density of some current is equal to 0. We define all these notions to finally prove that it's 0, and then we deduce the theorem. Okay, so another application which is also interesting. So you take any dominant meromorphic maps or compact Taylor manifold, or you can take correspondence also. And then this map is always an Artin major map in the following sense. So you consider the set of isolated periodic points, because the set of periodic points could have positive dimension, but we only count isolated periodic points. And the number of isolated points is goes at most exponential fast when the period goes to infinity. So this number is at most exponential. You can have a more precise estimate. And if you have more hypotheses on F, you can have more precise estimates. So actually it's not obvious, because the dimension of the you might have varieties of periodic points. So the contribution of if you try to use the Lefschetz fixed point theorem, you have the contribution of positive dimension set. So it's not clear. if you consider the case of real setting, even take a smooth real map, actually the theorem is wrong. So according to Kaloshin and other people, this number can grow as fast as we want. It's very unexpected because at the beginning people believe that everything should be bounded by entropy or something like that, but it's not the case in the real setting. In the complex setting, it's true. Okay, so I don't know if my time is almost finished. Okay, so we can develop the theory for d-bar closed current and show some uniqueness theorem for foliation. So we have generic foliation on Kähler surface. Then you have a unique positive DDC closed current of mass 1 directed by F, and then all leads are equidistributed on this. Okay, maybe I have to skip this. Let's open question. So here, related to the Maillet question, we have the following. So I have a sequence of T currents. Assume that Tk converging to T, and I have another current S. I assume that there is some intersection, nice intersection as you want. But what I want here is that the limit of intersection is equal to intersection of limit, basically. It's wrong in general. It's related to the transversality of currents of the intersection. But okay, the problem seems to is I don't have yes solution to this problem. And also we want to consider the speed of convergence. It's open, and the motivation here is to consider the equidistribution problem in a more general case. So for periodic point can be seen as the intersection of graph of Fk with the diagonal. So intersection of the graph of map with diagonal give you the set of fixed points or periodic points. And then you have the graph of the sequence of graph converts to in the sense of current to something, but you want that the intersection is diagonal converts to the intersection of the limit. It's not clear at all, and in the abstract setting of currents, it's wrong. Then there's a big question that we still have no solution, but following this strategy, we can do something. Only for the moment is in dimension 1. So your famous theorem by Bolin and Lewis, here you have the Julia set of a polynomial. We know that periodic points are equidistributed on the Julia set, is the boundary of this nice set. But now in collaboration with Kaufman, we can show that actually the speed of equidistribution is exponential. So the equidistribution is exponentially fast. It's not easy. But we follow the strategy. And it's in dimension 1, we easily go to dimension 2. And if you go to the tangent bundle and so on, you go to higher dimension very quickly. Okay, so another problem that I promise you to stay here is due to Jean-Pierre also. He asked me this question. So assume that you have a positive closed current T of mass 1 on a positive manifold X. And he wants to write T as T plus minus T minus, such that you can approach T plus and T minus using positive cycles. And you have to control the mass of T plus and T minus. You assume that there is no cohomological obstruction. Assume that everything is good for cohomology. No, because I think he always think about Hodge conjecture using currents. But assume that no cohomological obstruction. Can you approach currents by cycle in this way? And the famous theorem, or the theorem of Babai and her, they say that you cannot remove this T minus, even if you assume that there is no cohomological obstruction, you cannot remove this T minus. And I think Jean-Pierre asked me this question here some time ago. I think he first asked the question in some paper without T minus and a court exam given by her. And then he asked me this question. I have no idea. I tried something, but it didn't work. So I have no idea. So, okay, it's open for everyone. This question. Thank you so much for your attention.